As we can see, we can take derivatives of pretty much any polynomial function. Now that we've learned the product and quotient rule, we can take derivatives of rational functions. What happens if we would like to take the derivative of a function more than once? Well, if y equals f of x, then we can, when we take the derivative, we call this the first derivative. And this has a specific geometric interpretation, which is that in the graph, for the graph of the function y equals f of x, the first derivative at the point x will give you the slope of the line tangent to the graph of y equals f of x at x. So the first derivative, we can call it y prime, we can call it df dx, we can call it dy dx, we can call it d f of x, or we can call it dy. We did dy dx. We can call it f prime of x. Okay? So what if we take the derivative of the derivative? So we take our derivative function and we differentiate it again. Then we would have what we call the second derivative. We would call that y double prime, or d2f dx squared. I don't know why they call it squared, but d2y dy dx squared, d2 f of x, or f double prime of x. Well, if we can take it 2 times, we can also take it a 3rd time. So if we have the third derivative, that would be y triple prime, which is d3f dx cubed, which is d2 d3y dx cubed, which could be d3 of f of x, or f triple prime of x. As you can see, we can kind of carry on with this pretty much infinitely. So we can get the 4th derivative, or y quadruple prime, which is d to the 4f dx to the 4th, which is d4y dx to the 4th, which is d4 f of x, or f 1, 2, 3, 4 prime. Okay, and as you can see, we can clearly keep on going as long as we want. Okay, so to find the second derivative, we take the derivative of the first derivative. Okay, and we can go all the way down to what we would say y to the n, the nth derivative. Now let's look at a quick example. So if you can take a derivative, you can usually take a second derivative and a third derivative and a fourth derivative. Most functions, taking the derivative or multiple derivatives makes it simpler. Anything that's a rational function with fractions, it's going to make it a little bit more challenging because you have to use the quotient rule. So let's look at our first example. So find the 5th derivative of f of x equals 3x to the 4th plus 2x cubed minus 5x squared plus 7x minus 1. So we have f prime of x equals 12x cubed plus 6x squared minus 10x plus 7. And f double prime of x, we'll take the derivative again. So 3 times 12 is 36, so we get 36x squared plus 12x minus 10. And then we will take the third derivative. Unfortunately, there's no shortcuts. You just have to take, if you want to take the 5th derivative, you take the first, then the second, then the third, then the 4th, then the 5th. So we've got 36x squared, which is 72x plus 12. The fourth derivative is going to be just 72, and the fifth derivative is going to be 0. So all of that work just to find out that our fifth derivative is 0. So let's look at a question that's a little bit more interesting. Okay. So if f of x is equal to 1 over x, we want to find the first 4 derivatives and an expression for the nth derivative. Derivative. Then we're going to find the 2031st derivative of x. Okay, so let's look at the first 4 derivatives. And actually, this is a good step to take because we are going to need to look for a pattern. And pattern recognition is one of those things that is throughout all mathematics. You are always going to need to be able to find patterns. So f of x is x to the minus 1. And we're going to use a power because that allows us to use our power rule. So f prime of x is negative x to the minus 2. And I'm just going to write this as negative 1 times x to the minus 2. And so this is like kind of our 0th derivative, just our regular function. This is our first derivative, and this is going to be important because we want to link our pattern to which ordinal number it is. So whether it's first, second, third, fourth, we want to link it to that 1, 2, 3, 4 in order to come up with some kind of expression for the nth derivative. So we have f double prime of x, this is our second derivative, is equal to positive, we're going to multiply positive 2x to the minus 3. We're dropping the power by 1 each time, okay, which is equal to negative 1 times negative 2 times x to the minus 3. We can see our third derivative, f triple prime of x equals negative 6x to the negative 4. It's actually more useful to see that that is equal to negative 1 times negative 2 that we started with times a negative 3, x to the minus 4. And our fourth derivative, we're asked to find the first 4, and hopefully this will give us enough to develop a pattern, is positive 24, x to the negative 5, which is negative 1, we multiplied by negative 2, we multiplied by negative 3, we multiplied by negative 4, and we have an x to the negative 5. We've multiplied by everything up to. So we have a way of writing all these numbers multiplied. So what I'm going to do is I'm going to think of this, instead of thinking of this as negative 1 times negative 2, I'm going to think of this as negative 1 to the power of 4. I'm going to pull out a negative 1 times 1 times 2 times 3 times 4. Okay, so this, when we're multiplying numbers together in order, starting with 1, we can actually rewrite this as 4 factorial. So the exclamation mark means you take that number and multiply it to every counting number below it all the way down to 1. So 4 factorial would be 4 times 3 times 2 times 1. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we notice that we can do that for any of these. So this one is equal to negative 1 to the power of 1 times 1 factorial times x to the minus 2. This one is equal to negative 1 squared. See, we're multiplying by a negative twice times 2 factorial x to the minus 3. This one is equal to negative 1 cubed times 3 factorial x to the minus 4. And this one is equal to negative 1 to the 4th times 4 factorial times x to the minus 5. So now what we're going to do is we've got this in a pattern. So we're getting bigger by 1. The number we're taking the factorial of is getting bigger by 1. The number here is getting smaller by 1 each time. Okay, so now what we want to do is we want to try to figure out what the nth term is. Okay, so what I do is I take a look and I look at my numbers. So my 4, 4, 4. N is going to have an n wherever there is a 4. So my nth term, which is my fn of x, is going to be equal to negative 1 to the power of n. We're going to multiply by negative 1 n times. We're going to multiply by n factorial because we can see we started multiplying by 1, by 2, by 3. This is just going to continue. Next time we'll multiply by negative 5. Time after we'll multiply by negative 6. And we are going to have x to the power. Notice here, this is a negative number, but it's not negative 4, it's negative 5. When we had 3, it was negative 4. When we had 2, it was negative 1. So it's always 1 less than the negative of our ordinal or our counting number. So this is going to be negative n, but 1 less that, or negative n minus 1. Or you can put negative in bracket n plus 1, up to you. Okay, so we can now use this formula to calculate the 2031st derivative without having to take the derivative 2031 times. So negative 1 to the power of n, this is an odd number. If n is odd, it's positive. If n is odd, it's going to be negative 1. If n is even, it would be positive 1. So in this case, it would be negative 1. Okay, times n factorial, so negative 1 times 2031 factorial. And then x is going to be to the negative 2031 minus 1, or x to the negative 2032. So that 2031 factorial is an exceedingly large number. I have no desire to multiply that out, and neither should you. So at this stage, we've given enough information. We have found our 2031st derivative.